Download this code from codegive.com, link in the description below. OK, let's dive deep into interfaces and error handling in Go, two fundamental concepts for writing robust and maintainable Go code. Interfaces in Go. A. What are interfaces? At their core, interfaces in Go define a contract or a behavior. They specify a set of methods that a type must implement to be considered to satisfy or implement the interface. Go doesn't have explicit inheritance like some other languages. Instead, types implement interfaces implicitly. If a type defines all the methods required by an interface, it automatically implements that interface. Think of an interface as a blueprint for how something behaves, rather than what it is. It focuses on what a type does, not necessarily what it is. B. Why use interfaces? 1. Abstraction and decoupling. Interfaces allow you to write code that works with any type that satisfies a particular interface, without needing to know the specific concrete type. This decouples your code, making it more modular and easier to change or extend. You can swap out different implementations of the same interface without affecting the rest of your program. 2. Polymorphism. Interfaces enable polymorphism, the ability to treat different types in a uniform way. You can have a slice of interfaces, and each element in the slice can be a different type, as long as they all implement the same interface. 3. Testability. Interfaces make it easier to write unit tests. You can create mock implementations of interfaces to isolate the code you're testing and control its dependencies. 4. Code reusability. Interfaces promote code reuse. Functions or methods that accept interfaces can operate on a wider range of types, reducing the need for duplicated code. C. Defining interfaces. Here's how you define an interface in Go. Type interface name interface. This declares a new interface type named interface name. Method name 1, parameter 1 type 1, parameter 2 type 2, return type 1. This is a method signature. It specifies the method name, the types and names of the parameters, and the return type. If a method doesn't return anything, the return type is omitted, or you can explicitly use, for no return values. A type implements the interface if it provides methods with exactly the same names, parameter lists, types and order, and return types as defined in the interface. D. Example, the io.reader interface. The io.reader interface from the standard library is a classic example. This interface defines a single method called read. The read method takes a byte slice, byte, as input, which is where the data will be read into. It returns two values. N int, the number of bytes read. Error, an error value, or nil if the read was successful. Any type that has a read method with the signature automatically implements the io.reader interface. Examples include files, os.file, network connections, net.con, and strings, strings.reader. Implementing interfaces. Let's create a simple example to illustrate how types implement interfaces. Explanation *. 1. Shape interface *. We define the shape interface with two methods, area, and perimeter. 2. Circle and rectangle types *. We define two struct types, circle and rectangle. 3. Interface implementation *. Both circle and rectangle implement the shape interface because they have methods named area and perimeter, with the correct signatures, no parameters, float 64 return type. 4. Print shape info function *. This function accepts a shape interface as an argument. It can work with any type that implements the shape interface, without needing to know whether it's a circle, a rectangle, or something else entirely. 5. Polymorphism * in the main function, we create instances of circle and rectangle and pass them to print shape info. The print shape info function correctly calls the appropriate area and perimeter methods for each type. We also demonstrate using a slice of shape interfaces. Empty interface, interface. The empty interface, interface, is a special type of interface that has no methods. This means that every type in Go implements the empty interface. The print anything function can accept any value because any type implicitly implements the empty interface. However, you generally need to use type assertions or type switches, discussed below, to work with the underlying value of an interface. Type assertions and type switches. Since an interface only defines behavior, you sometimes need to get back the underlying concrete type. Go provides two mechanisms for this. One, type assertion *. A type assertion is used to extract the underlying concrete value from an interface. Value, OK equals I, my type. This attempts to assert that the interface I holds a value of type my type. Value will be the value of type my type if the assertion is successful. OK will be true if the assertion is successful, and false otherwise. This is called the OK idiom. It's the safe way to do type assertions. Value equals I, my type, this is the unsafe version. If the interface I does not hold a value of type my type, the program will panic, crash. Use this version only if you are absolutely sure that the interface holds the correct type. 2. Type switch *. A type switch is used to check the type of an interface value against multiple possible types. The switch V equals I, type, syntax performs a type assertion within the switch statement. Each case checks if the interface I holds a value of a specific type. The V variable within each case is the value of the interface, asserted to be of that type. The default case is executed if the interface does not hold a value of any of the specified types. 2. Error handling in Go. Why error handling matters. Robust error handling is crucial for creating reliable and maintainable software. It allows your program to gracefully handle unexpected situations, prevent crashes, and provide helpful information to the user or the system administrator for debugging. Ignoring errors can lead to silent failures, data corruption, and security vulnerabilities. B. The error interface. Go uses the error interface to represent errors. It's defined as the error interface requires a single method, error, string, which returns a human-readable string representation of the error. See returning errors. Go functions commonly return multiple values, including an error as the last return value. This is the standard way to indicate whether a function call was successful or encountered an error. Explanation *. 1. Return values *. The function my function returns two values, an int, the result, and an error. 2. Error condition *. If the input is negative, an error is created using fmt.error. fmt.error is a convenient function for creating formatted error strings. 3. Error handling *. The function returns 0, a default value for the result, and the newly created error. 4. Successful execution *. If the input is valid, the function calculates the result and returns it along with nil, which indicates that no error occurred. Nil is the zero value for the error interface. D. Handling errors. The caller of a function that returns an error should always check the error value. Explanation *. 1. Checking for errors *. After calling parseInt, we check if error is nil. If it's not nil, it means an error occurred. 2. Error handling *. In the error case, we print the error message to the console and then exit the program using return. In a real-world application, you might log the error, retry the operation, or take some other corrective action. 3 wrapping errors asterisk the fmt.error failed to parse integer, %w, error, uses the %w verb to wrap the original error. This preserves the original error's information and allows you to inspect the error chain. For successful case asterisk if error is nil, it means the function call was successful, and we can use the number value. Error wrapping and inspection. Go 1.13 introduced enhanced error handling with error wrapping and inspection, using the errors package. 1 Wrapping errors asterisk as seen above, you can wrap errors using fmt.error with the %w verb. This creates an error chain, preserving the context of the original error. 2 Inspecting errors asterisk the errors package provides functions for inspecting the error chain. Asterisk errors.is, error, target, checks if the error, or any error in its chain, is equal to target. You can compare against sentinel errors, predefined error values. Asterisk errors.as, error, target, tries to find an error in the chain that matches the type of target. If found, it sets target to the matching error and returns true. Explanation asterisk. 1 Sentinel error asterisk error not found is a sentinel error. Sentinel errors are predefined error values that you can compare against using errors.is. 2 Error wrapping asterisk load file wraps the os.error not exist error with error not found. 3 Errors.is asterisk the main function uses errors.is to check if the error chain contains error not found. 4 Errors.as asterisk the main function uses errors.as to extract the os.path error from the error chain. Errors.as requires you to pass a pointer to a variable of the type you want to extract. F. Custom error types. You can define your own custom error types by creating a struct that implements the error interface, i.e., has an error string method. This allows you to include additional information in the error. Explanation asterisk. 1 MyCustomError struct asterisk we define a struct MyCustomError with fields for an error code and a message. 2 Error method asterisk we implement the error method for MyCustomError, which returns a formatted error string. 3 Using the custom error asterisk the dosomething function returns a MyCustomError instance when an error occurs. 4 Type assertion asterisk in main, we use a type assertion to check if the error is a MyCustomError and, if so, access its code and message fields. G. Panic and recover, use with caution. Asterisk panic. A panic is a runtime error that causes the program to stop normal execution. It's similar to an exception in other languages. Panics are typically used for unrecoverable errors or programming errors. Asterisk recover, the recover function can be used to regain control after a panic. It can only be called from within a defer function. It returns the value passed to panic, or nil if there was no panic. Explanation asterisk. 1 Defer function asterisk the defer keyword schedules a function to be called after the surrounding function returns. In this case, the anonymous function will be called when myPanic returns, regardless of whether a panic occurred. 2 Recover, asterisk inside the deferred function, recover, is called. If a panic occurred, recover, returns the value passed to panic, and the program continues execution. If no panic occurred, recover, returns nil. 3 Panic, asterisk if val is negative, panic, is called, which stops normal execution. 4 Resumption asterisk the recover, function allows the program to continue after the panic. The program continues, line in main will be printed. Important notes about panic and recover asterisk. Use sparingly. Panic and recover are powerful tools, but they should be used sparingly. Overuse can make your code harder to understand and debug. It's generally better to handle errors explicitly using the error interface. Recovering only in top-level functions. It's best to recover from panics only in top-level functions, like the main function in a server application, to prevent the entire application from crashing. Purpose. Primarily, panic is intended for unexpected, unrecoverable situations, or developer errors that should be fixed. It is not meant to be used as a regular error handling mechanism. 3. Best practices for interfaces and error handling. Design interfaces carefully. Define interfaces based on the behavior you need, not on the specific types you have. Start with small, focused interfaces. Keep interfaces small. Prefer smaller, more granular interfaces. The smaller the interface, the easier it is to implement and the more flexible it is. Return errors consistently. Always return an error value from functions that can fail. Handle errors promptly. Check for errors immediately after calling a function that can return an error. Provide informative error messages. Make sure your error messages are clear, concise, and helpful for debugging. Include context about where the error occurred. Wrap errors to preserve context. Use error wrapping to maintain the original error information. Use errors.is and errors.as for error inspection. Use the errors package for robust error inspection. Avoid panic and recover except in specific situations. Limit panic and recover to exceptional cases and use them carefully. Consider using linters. Use linters like error check to help you identify unhandled errors in your code. GoVet also has helpful checks. Test your error handling. Write unit tests to ensure that your error handling logic is working correctly. Test both successful and error scenarios. 4. Common error handling patterns. Logging errors. Log errors to a file or a centralized logging system for monitoring and debugging. Returning errors to the user. Web applications. In web applications, return appropriate HTTP status codes and user-friendly error messages. Retrying operations. For transient errors, example network issues, consider retrying the operation. Conclusion. Interfaces and error handling are essential parts of writing clean, robust, and maintainable Go code. By using interfaces effectively, you can create more flexible and decoupled systems. By following best practices for error handling, you can ensure that your programs handle unexpected situations gracefully and provide valuable information for debugging. Understanding these concepts is critical for any Go developer. Remember to practice these principles to become proficient in writing high-quality Go applications.